Hey everyone, welcome to video 1-4A. We're going to be talking about introducing the idea of proof in this section. So a couple new vocabulary words here in our Explore. I'm on page 45. The first one is a conjecture, and a conjecture is just basically a statement that you are trying to prove whether it's true or not. You can use inductive or deductive reasoning to prove that it's true. Inductive reasoning is basically showing that it's true because a whole bunch of cases that you prove one right after another are true. And then deductive reasoning is using logic to draw conclusions by maybe even using some algebraic steps and things like that. So the very first thing we're going to do is we're going to try to prove this conjecture that the sum of three consecutive counting numbers is going to, we're going to prove that it's divisible by 3, okay? So the first thing we're going to do, and we're just going to do it inductively, is just take a couple of cases here. Part A asks us to write a sum to represent the first three consecutive counting numbers, and that's going to be starting with 1. So 1, 2, 3. And we'll write that as 1 plus 2 plus 3. What is that equal to? Well, that's equal to 6. Is that sum, 6, divisible by 3? Well, yeah. 6 divided by 3 does go in evenly, gets to be 2, so that's yes. Okay, part C says write the sum of the next three consecutive counting numbers starting with 2. So instead of 1, 2, 3, we're going to do 2 plus 3 plus 4. And in that case, you guys, we get 9. Interesting. Is that sum divisible by 3? Yes. So inductive reasoning here, we've done a couple of different cases and we've gotten the same outcome. Inductive reasoning would say, okay, the sum of any three consecutive counting numbers is divisible by 3. Now, we've only proven it, though, for 2 cases. So inductive reasoning might get us started, but deductive reasoning, using our logic and using, algebra possibly, or things that we know to already be true, is the best way to prove it, okay? So we're talking now about this new thing. Remember I talked about theorem. There's our word there, T-H-E-O-R-E-M. It's a statement that we can prove is true using a series of logical steps, and this is deductive reasoning here. So now we're going to do the same conjecture about adding 3 consecutive counting numbers, but instead of using specific cases, we're going to use a general case, an algebraic case, if you will, and we're going to use some different steps to prove it, okay? So for part F, it says let the 3 consecutive counting numbers be represented by, now notice they start us not with a number, but with a variable n, and then the next number up would be n plus 1 more, or n plus 1, and then the third number in the 3 consecutive counting numbers would be n plus 2. Part G says then, if I add all 3 of those algebraic expressions together, I have 1n, 2n, and then another n here, so 3n, plus what? Well, plus 1 and 2 are the only other 2 constant pieces, so those are going to be 3n plus 3, okay? Go to the next page. In part H, we're saying, okay, 3n plus 3 can be factored. Remember, factoring is taking a common divisor out to the outside there, and if we factor a 3 out of this expression here, that is going to be like dividing it mentally by 3, but we don't let the 3 disappear. We keep it on the outside. So that it's factored as 3 parentheses. What would be left if I were to divide 3 into each one of these? That would just be n and then plus 1. So then in I, the expression 3 parentheses n plus 1 is what we just came up with, is divisible by 3 for any value of n, okay? Because that 3 is a factor, that means it's divisible by 3. And then part J says, recall the conjecture the sum of three consecutive counting numbers is divisible by 3, and now look at the steps in our deductive reasoning. What did we do? We added some things together, we divided out or factored out, and we were able to see with logic that this is always going to be true. Quick little discussion here. Number 1, excuse me, new vocabulary word. Number 1 talks about a counterexample as an example that shows that a conjecture is actually not true or is false. Question is, do you think counterexamples are used mainly in inductive reasoning or in deductive reasoning? Well, anytime you're talking about a specific example, that's going to be inductive reasoning. Then number 2, suppose you use deductive reasoning to show that an angle is not acute. Can you conclude that the angle is obtuse? Are we able to say if it's not acute that it's always obtuse? No, because we can provide a counterexample of an angle that is not acute but also not obtuse. For example, a right angle. A right angle is not acute, but just because it's not acute does not mean that it has to be obtuse. You could also say a straight angle. Okay, so those are some counterexamples, inductive reasoning examples that prove that that conjecture is not true. And all you have to do for a counterexample is to prove one case where it's not true, and then the whole thing is not true. Okay? All right, let's go through some conditional statements here at the bottom of the page. A conditional statement is a statement that can be written in the form if P, then Q. So P is the hypothesis, we call, and Q is the conclusion. Two parts to a statement, okay, a logical statement that can be written in if P, then Q. For example, in the conditional statement, if 3x minus 5 equals 13, then x equals 6. The hypothesis is this first part that comes after the if, and then is the second part, and that is what we call the conclusion. Okay? So most of what we call the properties of equality in algebra can be written as conditional statements. All of the ifs are the same as you see here going down the table. If we have two numbers that are the same, A equals B, okay, then we can do certain things to them algebraically or numerically as long as we do the same thing to both sides of the equation. This is what Algebra 1, you guys, was completely built on. We can add a number to both sides, we can subtract a number from both sides, we can multiply on both sides and divide on both sides. So those are the three basic just arithmetic ones. And so you can see how that's expressed. If A is originally equal to B, then A plus C is equal to B plus C. So anytime we add a number to both sides, we're using this name here, the addition property of equality. Same thing with all the other three. Then we get to 4 more properties at the bottom here that we are going to be using. A reflexive property of equality just simply says that a number or a value is equal to itself. The symmetric property of equality says if A equals B, then B equals A. In other words, you can flip this statement around. The transitive property of equality says if I have 3 things that are related, A, B, and C, and A is equal to B, but then B is equal to C, something else, then I can kind of skip the middleman B here and just say A is the same thing as C. That's called the transitive property. And then finally the substitution property. If, again, we start with A equals B, then B can be put into any expression for A. That's called substitution. Okay? So what we're going to do on page 47 is we're going to look through these examples and see how they have justified moving to each additional step. This is going to be important for you as you get to geometric proof, so we're just kind of introducing it with the idea of algebra, okay? In part A, they've done the whole thing for us, so let's just talk through it. If this is my original statement, we're going to solve the equation, and we're going to justify each step. So from 14 equals 3x minus 4 to now 18 equals 3x, the question is, what did we do to both sides? Well, we know algebraically we had to get rid of that 4 by adding 4 to both sides. So that's why we have the addition property of equality there. Then the next question is to go from 18 equals 3x to 6 equals x. What did we do? Well, in that case, we divided both sides by the number in front of the variable, the coefficient 3, and we got just 6 equals x. Division property of equality was used there. And then notice 6 equals x becomes x equals 6 because most algebra books like to keep that variable on the left-hand side. Don't ask me why. But again, flipping that statement around is just using the symmetric property. Okay, so that's justifying each one of the steps that we took there. Let's see if we can do that a little bit more with fill-ins in B. We start with 9 equals 17 minus 4x. And notice in the next step down, the 17 has been gotten rid of. How did we do that? Well, we must have subtracted the 17 on both sides. And so that's the subtraction property, and I'm just going to abbreviate it here, of equality. What do we get when we do that? We get 9 minus 17 is negative 8, and that's just equal to negative 4x. Of course, what we did next is divide by that coefficient, and so that's the division property of equality that gives us just positive 2 equals negative 4x. And then we get to turn that around with the symmetric property. Same steps as above. They won't always be the same, but you're going to get through the idea basically of going through and justifying each step. Okay? All right, I want you to pause here from taking some notes and do some of these your turn questions. You have 3, 4, and 5 that you need to work through. It asks you to write each statement as a conditional, so remember that's the if P then Q. See if you can come up with an original condition or hypothesis, and then Q the conclusion and write that kind of in 2 pieces. Each one of these statements, 3, 4, and then 5 asks you to use some deductive reasoning. Okay? On number 6 also, I want you to go through and look at the properties that are used here between the if and then the then piece of each conditional that's shown to you. So, 4 quick your turns there before you move on, okay?